Hi, we have four members in our team, and while developing n-by-n systolic accelerator, which will take 16 bits of input and leave 32 bits of output. Our systolic will be of fixed point. I'll tell you the reason of floating point input later on. For example, we have chose 4x4 systolic to let you understand the design. And for interfacing, we will be joined with a divided protocol, or we will synthesize it on FPGA as well, and then integrate it on RISC-V processor or run a machine learning. And so it's a top-level item having processing elements, data feeders, input and output data part. So first of all, we have processing element, which will take 16 bits of floating point input and then pass it to next processing element, and also a result of 32 bits MAC unit. So the A out and B out I'll show you in the diagram. So that's all the A out and that's all the B out, which will go into next processing element. You can see we have a MET unit inside it, which will leave 32 bits of fixed point output and which will store in Y out, and we have our counter as well, which will leave as a valid out signal. So the counter will take the done signal from MET unit and a valid out signal. I have named it with enable 1. For a 4x4 systolic, it will count 8 times from 0 to 7. And why 3 bits here? Because 7 in binary is 111, which at least need 3 bits of input. We have a all date as well, which on enable Y. Enable Y means count have been done, or on reset the selector of months chooses 1, and so we will let 0 on the register. Otherwise, we will let the done signal and will count for the next, and that goes up till 7. So we have used resistors, multiple resistors in our design, and we have chooses loaded as that on reset it will scroll 0. Otherwise, it will scroll data on resistor, and on next the dot sider it will give us the actual data on the data out. So inside processing element, we have MET unit, which will take 2 floating point inputs and give us 132 bits fixed point input. That 32 bits contains 16 bits of integer part and 16 bits of fractional part, and done as a signal which that is that the output has been computed. So the reason of floating point input is that we have used approximate multiplier, which deals with the floating point numbers. We have been using approximate multiplier so that it will take less resources and LUT, so that we can synthesize it on FPGA as well. Also, it will take less area for triple one as well, so that finally it can easily be ready for the tape out. So since our systolic is a fixed point, so we will convert it into 16 bits of fixed point number, and then after accumulation we will convert into 32 bits of fixed point number. So that's the design diagram of MET unit. The input will first be stored in the resistors and then passes into approximate multiplier and then convert into fixed point, and then after accumulation we will let all final out. So it's the STG, and to be noted here is the STG of just accumulation part, because there's no need of a separate STG for multiplier since we have been using an approximate one. For accumulation, it waits for the valid signal. As soon as the valid becomes high, it will start accumulating, and on valid equals 0 it will be in the idle state. After accumulation, done signal will become high and it will in the done state, and after that we will get the final result, which will be stored in Y. So I have done with the processing element. You have seen the data feeders here. The purpose of it that we are getting 7 elements at a time. Why 7 elements? Because of systolic architecture. You can see that by systolic architecture on each part, maximum number of elements is 7. So that's why we are feeding 7 numbers at a time. So the purpose of data feeders is that we are getting 7 elements at a time, and it will pass one element one by one to the processing element for final computation. And so it's a block diagram. We have getting 1 base of numbers, since 7 elements and each element is of 16 bit, and letting 16 bits of output. The output will go into processing element. We have using shift here. As soon as the load signal becomes high, it feeds 112 bit of elements, means 7 elements into resistor, and as soon as it will let shift, it will write shift 16 bits of element, means 1 element to the processing element. Okay, so till now we have done with the systolic array, and then we have interfacing obviously. So it's the input and output data part, and it's the overall interfacing structure. Here is a systolic array, and we have using ready valid, and so our interfacing has been into handshake model basically. So that RV is nothing but a resistor which operates on ready valid architecture. It will leave the same output as the input is, but the twist here is that it will first see the ready and valid signal. When the baud signal was high, we have named a signal called enable data transfer. It becomes high, and the exact value of data throws in the resistor, which on the load side we will let the data out. Also on enable data transfer, we will make all months high and we will let transfer done signal, which indicates that we have received the data up. And it's the SRC which operates on the same principle which I have stated earlier. So let's deep dive into input data part. We have been taking 128 bits of input, means the user have to leave 128 bits of data as input, which means it will take first 4 elements of the rows of A and next 4 elements of the columns of B. Since you know systolic is like that, we have 4 rows of A here and 4 columns of B here from the input matrices. So we have designed in such a way that it will take first 4 elements of A rows and first 4 B columns, and so we are feeding 8 elements at a time, and so 8 into 16 total is 128. So in input data part, we will basically that separated are each row and each column of A and B respectively. It has been shown in the below diagram as well. It's A and it's B, which we will let after input manager. So the question here is that how we will find out the row or column number. So we have used a daemons over here, which will operate on selector pins of rows and columns. We have named it R cell and C cell. R cell is the selector pins of the rows of A, and C cell are the selector pin of the columns of B matrix. And to feed the exact or specific row or column into the systolic array, we have used list count based plots. So in the alter, it will shed for for the row number 1, it will shed for if it was 0, then it's the column number 1 of B and row number 1 of A. If it's equal 1, it will be the column number 2 of B and row number 2 of A, and so on. Lastly, we have output data part where we let 512 bits. Why 512 bits? Since we have 16 processing element in a 4x4 systolic, and each processing element output is 32 bits. So 32 into 16 is 512, and after that we will access to 4 bits as output. So finally in the form of 4x4 matrix or an array. So for this paper we are again using shift over here, which are operating on the same purpose as the data feeders. So here's the overall diagram of our system and its strategy through which we are writing our RTL and will simulate it via test benches. So for with progress update we have done with design diagrams, FSM, strategy, and RTL and verification of unit and synthesis of main as well on FPGA. And right now we are doing RTL and verification of modules level, and after that we will synthesize the whole into FPGA and then we'll do physical design. And it was our proposed timeline. And lastly, I have given an example of 4x4 systolic, and we are making an n by n, so we will use these approaches for the numbers I have